Welcome to the course. This is the second course in a two-part series looking at analytical modelling of plate and shell structures. In this course, we shift our focus onto shell structures. When you finish the course, you'll understand how to analyse shell structures that conform to common geometries, such as spheres, cones, cylinders, and hyperboloids. This course continues in the same vein as part 1. Initially, we'll focus on developing a toolbox of equations that we can use to model the shell's behaviour. Then we'll apply these new tools in a range of case study analyses. Now, what makes shells such efficient structures is their ability to resist external loading by developing membrane stresses. When a shell is well designed, bending stresses are minimised in favour of direct membrane stresses. For this reason, we focus exclusively on membrane behaviour in this course. While localised bending is almost always unavoidable and can't be ignored in a production level design, it'll generally be of secondary importance. In addition to helping you develop a good first principles understanding of shell behaviour, my other main aim with this course, just like in part 1, is to help you develop the tools and techniques to work with symbolic math in Python. I can't overstate how much of an unlock it is for your study of engineering to be able to work with and navigate mathematics through programming. We'll see this as we move through the course and unlock the dense mathematics that shell behaviour is typically shrouded in. Okay, next I want to give you a quick overview of the game plan for the rest of the course. In the following 2 lectures in this section, we'll recap a couple of concepts we've already covered in the previous course on plate analysis. If you've already completed part 1, you can skip ahead to section 2. In section 2, we'll develop the fundamental equations we'll use for the rest of the course. Section 2 is very much the foundation of everything else that follows. We'll build up a collection of equations that will allow us to model the membrane stress distribution and the membrane displacements. This section has a lot of theory in it, but time spent here will pay off down the line. In section 3, we'll put our equations to work on spherical shells. Now, the spherical shell is a great geometry to start with because of its constant curvature. This allows us to simplify our equations from section 2 and focus on the analysis workflow without getting too deep into the weeds. In section 4, we'll continue to focus on spherical shells, but this time we go on a bit of a tangent investigating how to model the influence of a retained liquid. Since shells are often used as liquid and gas tanks, this is a worthwhile detour. By the time we reach section 5, we'll have plenty of spherical shell analysis under our belt, and it'll be time to expand into other geometries. We'll look first at shells with zero Gaussian curvature. This means we focus on conical and cylindrical shells, and from here we move on to look at the hyperboloid, commonly seen in the form of a cooling tower. In the final section of the course, section 6, we'll take everything we've learned up to this point and bring it all together in the analysis of multi-shell or compound shell structures. By combining different shell geometries within a single structure, we dramatically increase the range of structures we can apply our models to. By the time you finish this section in particular, you'll really see the broad applicability of what you've been learning in the course. Now, all lectures have a dedicated discussion thread where you can post support requests. If you've got any questions as you work through the course, feel free to post them in the discussion thread for the relevant lecture. Then either myself or possibly another learner will respond. If your question relates to a specific part of a lecture, please provide a timestamp to help me respond as efficiently as possible. So just a quick note now on Python before we wrap up here. We'll use Python throughout the course as a means of visualizing the response of our shell structures and also as a tool for handling symbolic math. As with all engineering skills courses, you don't need to come to the course knowing Python. I'm a firm believer in learning by doing, so you'll pick up all the Python you need as you move through the course. If you've already completed part 1 on plate analysis, you'll have your Python environment already up and running, but if you're coming straight into this course without any Python experience, you can follow the links in the course text below this video. These will redirect you to other lectures that will walk you through setting up your local development environment. Okay, so that's the introduction and housekeeping covered. Now let's get stuck into the course.